Am I audible, sir?
Yes, you are.
Uh, Sir, here are the students who are listening to you, sir. So have a look, sir.
You are audible, but I can't see you. Ah, okay. Yes, that was coming now.
चालू नहीं है चालू नहीं है लाइट नहीं आ रहा है इस पे
That's fine. I could see a little bit. That's fine. Thank you. Thank you very much. I hope you can hear me and see me okay. So appreciate this invitation. Thank you so much. I have very fond memories of visiting right years ago or the pandemic, and it was great. So I'll be telling you today about some latest insights on black hole research. This will be a more public talk. Not a huge amount of detail. You're welcome to ask me details later on. I would appreciate some feedback on the talk. There is a QR code here, which you can use to access the feedback form, or I will also give you a link at the end of that. So please do take just 5 minutes to fill in that feedback form. Okay, so let's begin. I will be talking to you today about black holes, and I'll be dealing with several questions. What are black holes? Why are they interesting? Where are they? Where are the black holes? How big are they? Do they change in some way? And how do we study them? And what more remains to be found? Okay, that's what I'll be dealing with. Just very briefly about me, you already heard in the introduction, I was born in New Delhi. I came to the UK for my master's and PhD, and I went to Chile. It's an amazing country. I highly recommend it. They have lots of lovely telescopes in the Andes Mountains there. Well, just like the Himalayas, you have lovely telescopes up there. After Chile, I went to Japan for several reasons, but also because they launch lots of X-ray satellites, which I work on to understand black holes, before finally ending up back here in Chile. This was a very sort of nomadic path that I followed in my life, but the world is changing, and if I were born today, then I would probably do my research in astrophysics and a lot more freedom in some respects than abroad. So the world really is changing. Okay, so let's start with the details a little bit. What is a black hole? In this image of a black hole, this is the very first image, a real image of a black hole, if you want, that humanity ever gathered. This is in the M87 galaxy, which lies in the Virgo cluster. It's a supermassive black hole, which is at the center there, right at the center of this black circle in the middle of this donut. The bright donut is our clue that there is something falling into the black hole, which I will talk about in a second. So this was gathered by the Event Horizon Consortium, and you might have seen this before. If we were up close to this black hole, very, very close, you might see something like this, maybe. Nowadays, everyone has seen this movie, I hope, Interstellar. They use some very realistic graphics to try and understand what black holes look like. But what are we looking at here, really? Well, a black hole, there are many definitions depending upon what exactly you're talking about, but essentially a black hole is a point mass of infinite density. Okay. Infinitely dense point, which is enclosed by an event horizon. Okay. And that is causally disconnected from the rest of the universe. So what does that mean? Well, basically, a black hole, as far as we understand, as far as the equations tell us, is a point mass of infinite density, the singularity right at the center, essentially. But it is surrounded by this so-called boundary, if you want, a threshold called the event horizon. And anything that happens inside the event horizon, we cannot have any knowledge of that. Okay. The reason is because it takes the escape velocity from that region is faster than the speed of light. So no signal can hope to escape from there. You probably are all aware of these sorts of images nowadays. In particular, this is a very recent, beautiful image of the cosmos. This was released just a few weeks, well, actually a few months ago now, by the James Webb Space Telescope, the JWST Deep Field. It shows literally thousands of galaxies, maybe even tens of thousands, with some stars as well. But a beautiful image of the cosmos in the infrared. Okay, and as I said, there's lots of galaxies there. Where are the black holes in here? Well, you could gather the same image, not in infrared, but in a different waveband. And the previous speaker was just talking about multi-wavelength studies, so you know about this. If you could gather an image in X-rays instead, then this is what you would see. So this is an X-ray image deep image of the cosmos, very, very small area of sky. This is the Chandra deep field south image in this case. And every point of light that you can see here is a black hole, a supermassive black hole, just like we saw in M87, in which there's matter falling in. Before matter falls in, it becomes very hot, very bright, and that emits a lot of light, such as these X-rays that we see here. The different colors of light just tell you about different energies of X-rays. Don't worry about the colors. But basically, the universe, as you can see here, is literally filled with thousands and thousands, millions of black holes, literally, supermassive black holes in this case, all accreting, not all, a large fraction of them, somewhere between 10 and 30% of them, accreting material and glowing at any one time. Okay. If instead you were to gather an image not of the distant universe, but of our own galaxy, our own Milky Way galaxy, in X-rays, it might look something like this. Here you can see this is a plane of the Milky Way right in the center, and this is a 360-degree image all around the sky. You can see lots and lots of point sources, X-ray sources again. Most of them are black holes in our own Milky Way galaxy, or neutron stars in our own Milky Way galaxy. Okay, all of them again accreting matter. There's matter falling in, and before it falls down the event horizon, it becomes very hot, very bright, and that's what we are seeing. So we have black holes, these stellar mass the small black holes in our own Milky Way, and these supermassive black holes that are found in distant galaxies. Those are the two main varieties of black holes that we know of. How do black holes form? We still don't understand how the supermassive black holes form in detail. But as far as stellar mass black holes are concerned, this is what we think happens. So this is just a schematic representation of evolution of a star. And the main parameter that determines the star's life is its mass. So small stars evolve down a certain path, and large stars tend to evolve down a different path. Roughly speaking, this is, of course, just a very simplistic depiction. But you can see here, stars are born from collapsing gas clouds. And then if you happen to form a star here, small means something like our own sun, that will evolve on the main sequence. Maybe you know about the main sequence a little bit. And eventually it will turn into a red giant and then become a so-called planetary nebula, in which the outer layers will be shed. And what will be left at the center will be a white dwarf, which is just radiating away its hot energy and cooling down over literally, hundreds of billions of years, really. Conversely, if you have a star which is much, much more massive than our sun, that will follow a different path. It's because here the gravity is so strong that it evolves a star much more quickly. All the processes in the star must evolve much more quickly. A lot more energy is required to be able to balance the crushing force of gravity inside. So the star's fuel is consumed very, very quickly, and also it's much more violent. It turns into a very large supergiant star, in this case, depiction here. And ultimately that ends up in a big explosion, a supernova, in which the outer layers are explosively thrown out. And then what you end up with is either a neutron star or a black hole, depending upon the mass of the remnant at the center. And these are what you have been seeing in the previous images, except that when they accrete matter, then they glow brightly. That's what you've been seeing. This is I'm going to show you a movie. I hope it works. This is a movie created by NASA, and it's a depiction of a gravitational wave merger. So let the movie play. Okay, so what did we see here? We saw in this case two neutron stars actually that are orbiting each other. They are in a binary system, they are orbiting each other. These are really, really close together. And you saw them actually coming closer and closer together. They radiate away their energy as these waves that move outwards. These are the so-called gravitational waves that were detected a few years ago, and they got the Nobel Prize detected by the LIGO collaboration. I don't have time to go into that, unfortunately. It's an amazing discovery. And then when they merged at the instant of merger, what we saw was a black hole being formed right at the center. Two neutron stars merged, formed a black hole. And in that process, some of the outer layers were thrown out, shot outwards like these jets here. They went off into space. They formed these beautiful, amazing jets that we see. These are all very heavy elements, elements like gold, etc. These all come from neutron star mergers. So all the gold in your watches or in the jewelry that you might have or your parents might have, that all comes from neutron star mergers, which is quite an amazing discovery, I think. Just checking, can you still hear me okay? Everything going fine? I can see you now. Hello, everyone. Can you see me? Can you hear me? Okay. Okay, brilliant. Just checking that it's all working. Okay. Okay, so let's continue. Oh, sorry. So what you saw there was a merger of two compact objects, either neutron star or black hole. This is not playing. Another process by which black holes can grow and be born and grow. Oh, I don't know why it's stopping. Maybe just start it again. Let me just try again. Is this so-called accretion of matter. Basically, in this case, you have a star, a normal luminous star, something like our sun, which is orbiting around a black hole or a neutron star. Okay? And the outer layers are being shed. The outer layers of the star are being shed. They come in close to this black hole or neutron star. And because of conservation of angular momentum, they form a disk. And this disk, some of the material falls down through the center onto the compact object to make it grow. Some of the material is actually shot outwards before it and creates these beautiful jets that we see. So this process is a very steady growth process of accretion of matter that we've been discussing. So there's two processes that we know of how black holes can grow, either these big sort of singular mergers, if you want, and this steady accretion. So I want to binary systems because these are very non-intuitive systems. We don't really have a good grasp of them in everyday life. So how big are such binary systems, you might ask? This looks like, it's one star orbiting another big black hole 10 times the mass of our sun or something like that. So it looks like it's going to be very big. But compare this, you might like our solar system. So here, this graphic is a depiction of our own solar system. Here, this is our sun on the left, and these are all the planets you can see moving outwards. And so here, the distances are roughly to scale, approximately correct to scale. So in here, what are the distances? Maybe some of you know how far away is the Earth from the sun in light minutes. It's about 8 light minutes away, right? Whereas something like Neptune is roughly 4 light hours away. So it takes light from the sun, Neptune. They are very, very compact. This is only the separation here is only approximately 10 light seconds, just a few tens of light seconds at most in most of So remember, here we are talking seconds, so very, very small, much, much more compact, which is quite amazing if you think about it, that you can actually fit, one star around another former star, a very massive black hole in such a small area. And because they are so compact, these binary systems, they're very difficult to actually resolve. We can't actually make photographs to resolve all this structure in detail. Okay, if you were to actually place this, at typical distances in the Milky Way of a few thousand light years away, then you will need resolution powers of micro arc seconds. If there are some experts amongst you in astrophysics, maybe you understand what micro arc seconds is, but it is well, it's basically I think almost a billionth of a degree. So very, 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 very small angles. Okay. The effective magnification power will be something like 10 million or so if you wanted to resolve that. So it is still very difficult, just outside what we can actually do. But the next generation of telescopes might be able to. We've talked about the size of black holes. Let's talk a little bit about their power. So I'm sure you know the power is by fusion, nuclear fusion. Here we are talking about how efficient is how much generate. Well, I think this is only one of two equations in my talk here. So you all hopefully know E equals mc squared, Einstein's famous equation. So if you can cast these respective equations in terms of something like E equals mc squared or so, and then ask yourself, what is the efficiency of that process? So it turns out that in nuclear fusion, the efficiency is about 0.7%. Okay, so if you have two, say for example, 2 or 4 hydrogen nuclei, about that energy is mass is converted into energy that we can see, the heat and the light that we see. By contrast, when we talk about accretion, then the efficiency is something like 10% or so. So almost, more than 10 times more efficient, certainly easily much more. And that's only approximately. In some cases, it can go up to 40% or so even. So accretion power is very, very efficient. And if someday we can harness accretion power, then all our energy problems might be solved quite easily by just harnessing the power of black holes. Okay, where are black holes located? This shows you a depiction of the locations of known black hole systems, known and confirmed black hole systems in our own galaxy. So if we could travel above our galaxy and look down upon it, it might look something like this. The sun is located roughly there where the red dot is. And then you see some blue dots and some yellow dots. Those are different. These are all black holes, but there's different techniques to measure their distances. So don't worry about the different colors. But you can see that approximately speaking, they all cluster around the sun. And they're spread out roughly all the way to the galactic center. Okay. Distances are typically a few thousand light years away, roughly speaking. The nearest one that we know about is a few thousand light years away. In fact, there was one that was announced recently, which is probably just 1,000 light years away or so. So why are there no black holes on this side of the galaxy at the top? Or why are there no black holes at the bottom here on the other side? So this is not, don't think that this is some conspiracy of black holes being only close to the sun. This is actually just a so-called observational selection effect. Basically, we have not found black holes yet on the other side of the galaxy or in these regions. And that's simply because of various observational constraints that we have in our telescopes, etc., and also in the distribution of these objects. there's a lot of gas and dust in the Milky Way, which I'm sure you know about. You might have seen in previous talks. And also here you can see there are these spiral arms of gas and dust. These dust lanes actually obscure our view to the other side of the galaxy. We can't actually see objects easily that are present on the other side of the galaxy. And so we need even more powerful telescopes to be able to probe through all that gas and dust. And again, the next generation of telescopes will hopefully help a little bit to improve that. Oh yes, you are located there. Okay. Yes, and our galaxy is about 100,000 light years across. Okay. So how I told you about all these distances, a few thousand light years, etc. How do we measure these distances? We use actually the most reliable technique. Use very simple geometry, very simple trigonometry, nothing very complicated, and it's just triangulation, really. And so the idea here is that if you want to measure the distance to some star or any object in the sky, then all you need to do is you need to observe that object at different times. So, for example, when the Earth is here, for example, in August in its orbit around the sun, then you observe this star cluster, okay, and you look at the position of the star cluster relative to more distant objects, like very distant galaxies or distant quasars, etc. Then you wait a little bit and you take another measurement, maybe in this case 6 months later, okay, 6 months later or so, when the Earth is at the other side of its orbit. In this case, you can see that the relative angle, will have changed between you, the star cluster, and very distant objects. Okay, so by measuring this angle, if you know this angle of change, and if you know the Earth-Sun distance, you know your baseline here, then using very simple trigonometry, you can measure this distance just using sine of the angles, etc. Very, very easy. And people have been doing this for thousands of years here on Earth, and also this is what has been used to measure some of the most accurate distances to nearby stars for many, many years now. And this is a so-called parallax angle is what we measure in this case. The difficulty here is that we are because these distances are so large, and we're talking about, as I said, thousands of light years, the angles are incredibly small. Okay? So the angles that we need are less than a millionth of a degree in order to measure. And to do this, specialized instruments, very sensitive satellites. And it's only in the last few years that we have actually got good enough data that we are able to do this. And a lot of this data was recently gathered by the Gaia satellite, Europe's Gaia satellite. It's an amazing satellite. All the data are public, available online. Any one of you can go and analyze that data right now. You can just download it or determine the distance to any star that it's surveyed in the sky. But you really need something which can measure very, very, very accurate angles. So that's a challenge. Okay. Nevertheless, as I said, these sorts of separations, I talked about these 10 light seconds, that still remains out of reach, even for Gaia. It's very, very difficult to measure these accurately. So how do we study these accreting black holes? Well, here we use a different trick to do with the multiple wavelengths that you heard about before. So let's ask ourselves if we could actually study the structure of this accretion disk for going outwards. What would it look like? And you can imagine that as you get closer and closer in to the black hole, then the conditions become much more chaotic, much more violent. The orbital velocity becomes much, much faster. And the temperature also rises a lot more. You're deep in the gravitational potential well of this object. And so if you were to try and plot something like radius versus temperature, for example, you might end up with a graph, something like this. You can actually work this out using some simple theory of accretion of matter, conservation of mass as it flows inwards, and it turns out that this will be the sort of temperature profile or so. Okay. Now here, the temperature actually rises very, very steeply right in the center, which means that we cannot probe it using just a single satellite. We have to use different satellites to do this, many different satellites. And why is this? It's because in the center, when we go to the center, the temperatures are almost 10 million degrees, roughly speaking. Of course, it depends upon the black hole, but I'm just giving you an order of magnitude estimate for these binary systems. On the outside, the temperature might be something like 10,000 degrees only. So almost 10,000 times smaller, and 1,000 times smaller. Or this is something like the surface of our sun, 10,000 degrees, roughly speaking. Our sun is about 5,000. Whereas in the center, you're talking about some temperatures much higher. So if you want to probe the outskirts of this disk, then it's better to use a wavelength which corresponds to 10,000 degrees better. And if you know a little bit about black body radiation, then maybe you know that this will be better probed in the optical, in the ultraviolet, etc. Whereas 10 million degrees, there will be not much emission in the optical band. Okay, you have to really use much higher energies like X-rays. And so here, I just wanted to make sure you all understand that we are learning something new at every wavelength. This is an example to show you our own sun at different wavelengths. So this is infrared, optical, ultraviolet, and X-rays. All are images of our sun at actually approximately the same time, I think. But you can see here that the image of the sun changes dramatically, changes a lot from one wavelength to another. Here, for example, in the optical visible light, the sun looks very smooth, okay, except for these two small, maybe you can see, maybe not on your screen, I'm not sure, but there are two sunspots there, very small, look like small sunspots. In the infrared, the same sunspots, well, that sunspot there is very bright, okay, or very dark, actually, I should say it's very big. In the X-rays, that I think is the same sunspot, I believe, and basically it is much more active for some reason, okay? So what we are seeing here are different magnetically active regions of the sun, and the different emission processes at X-rays is different to optical, and it's different to infrared, etc. But if you had only the visible light image of the sun, you could not properly infer how active these sunspots are, for instance. You really need to go to much higher energies in order to understand this. So we really need the full electromagnetic spectrum, all the way from radio to infrared to X-rays and even more, to learn the full picture of what's happening in these systems. India has actually been contributing a lot in this regard, and I hope you know about the ASTROSAT mission, which was actually India's first multi-wavelength astronomy satellite, an amazing achievement. They were able to launch many different instruments together, focused quite heavily on X-rays, but also violet, and it's been gathering a lot of data on accreting black holes and doing a lot of good research. So I wish I had an ASTROSAT movie. I don't. Instead, I have a different movie, something similar to ASTROSAT. This was launched by NASA about 1 or maybe 15 years before ASTROSAT, I think. The RXTE mission, Rossi X-ray Timing Explorer. And this shows you, so it's a compiled data animation of all the data gathered by RXTE over time. Okay, so I'm going to play the movie, and you'll see lots of flashes of light. That's the first thing you see. You also see this blob that's moving around That's just the sun. Don't worry about that. We're not really bothered about the sun here. Instead, look at all these flashes as a function of time. So these are days. On different days, you can see different objects flashing, becoming brighter, becoming fainter, etc. And what are all these flashes and why are they changing? Well, again, these are these black holes and neutron stars, which are accreting matter. Because it's a very chaotic environment, the processes happening in the middle are they change every minute, every day. They can change, and so sometimes these objects can become very bright, very active, and you can see that sometimes there new ones appear in the background like there, and then they completely disappear. um, so by looking at these X-ray flashes, if you want, or looking at the variation in X-rays, you can learn a lot about how the matter is accreting onto these black holes and neutron stars. Even though we can't resolve them, we can piece together a lot of information as to what's happening just by studying this variability. And now I'm going to show you an even more extreme example of this. So here you will see on the left hand side, this is a real image of a black hole on the left hand side there at the top. And you will see a movie now of how this black hole changes in time, but not on the time scale of days, but on time scales of milliseconds. Okay, so this is what this movie will look like. I hope it works. Not working. Let me just try that again. Can you still see me? Yes, okay, fine. Yeah. If it doesn't work, I have another solution. Actually, I might be able to. This is also available on YouTube. Don't know why it's doing this. Sorry, just give me 1 second to try and sort this out. While that is restarting, let me show you the YouTube movie instead. So what I'll do is I will share my full screen. Okay. I hope you can see me. And so let's go see this. So this is an animation of a black hole system in our galaxy. It was made by our team, actually. And this is based on real data. I hope you can see it. If not, please someone unmute and say it. But anyway, here you can see variations in visible light, in this case, in X-rays. But the speed of the changes is the important thing. This movie has actually been slowed down by 10 times. Okay, so all these flashes are real, and they're not just real, but they're happening much faster than our eye. And each responds to something like 1,000 times the brightness of our own sun. So you have some object which is changing very rapidly, faster than the eye can see, and becoming much brighter than our sun, and then fading very quickly, all in the blink of an eye. Okay, so these objects are so extreme to see something like this for our own sun. Of course, if our sun were doing something like this, then life on Earth would be finished. Okay, stop that. Yes, this was made in collaboration with Ayuka and us. Right. Let's restart this. Where were we? Okay. So, what can we learn from this rapid flashing? Here, I want you to understand that the variability tells us about the characteristic size of these objects. And hopefully, this is obvious to all of you. But if not, I'll just take you through some very brief animation to tell you what this means. So, for example, imagine that we have some source of light. In this case, it's a bulb that's flashing relatively quickly, flashing quickly. If we could see it directly, then we would obviously see it flashing up and down very quickly. Okay, but let's imagine that this is actually, oh, okay, so that would be the direct light from it. Now let's imagine that instead of seeing the bulb directly, we can't see the bulb directly for some reason, but the bulb is actually surrounded by some kind of other material, some kind of screen, some kind of, there are these covers or globes around bulbs as well, like those snow globes, which make them a bit shady, for example. In space, this could correspond to some kind of a big structure like a disk or some kind of gas cloud, etc. Then what would happen? Well, the bulb is still varying very quickly up and down, and so light from it travels outwards until it hits the this covering screen, right? This globe. But what happens after that? After that, how is the light going to travel to us? That's what you need to think about. Well, the portion of the screen of this globe that is closest to us, that's what we will first see, right? Because light travels from here to us fastest. Then farther away points on the globe will be visible because light takes longer to reach us from them. And then even farther away points of the globe will be visible if light can travel through them. In some instances, then we'll start to see the backside, maybe obscured a little bit, but we will see it. Until finally we see the backside of the globe. So essentially, what has happened is that the flash of light from the center gets smeared out in time by the size of this globe. Okay, the larger the globe, the more is the smearing across the travel time of light. And so the simple equation which this translates to is that the inferred size of this screen, okay, has to be smaller than the speed of light that it takes for light to travel all across. So if we see variability with some characteristic time scale, t, okay, then you can infer a characteristic size of that object simply by using the speed of light. Very, very simple sort of scaling relation, if you want, but it is very powerful. Okay, and this tells you that for larger sizes, the effective variability will be slower, will be damped across a larger region. Okay, so keep that in mind. So here's the puzzle for you. We saw that very, very fast flashing of light on that YouTube video. Okay, much, much faster than the blink of an eye, like I said. And I also told you before that the typical sizes here that we're talking about are approximately 10 light seconds or so to the outer disk, which glows with that radiation. So what's happening here? We expect a size of 10 light seconds, but we are seeing variability on millisecond timescales, very, very fast. How is that possible? Because I told you that the size must be at least as big as the variability time. Okay, so what that essentially tells you is that this model is not quite correct. Okay, even though, or if this model is correct, there is something additional happening in these objects. Now it's working, finally. Okay, now you can see it. So you can see this really, really rapid, fast variation of light. The full scale there, y-axis scale, is something like factor of 3 or so. And so we see these very bright, very rapid flashes, much, much faster than 10 seconds or so. And we're trying to understand the origin of this variability. Okay, so I'll leave that. Uh, that's the main thing that I wanted to show you before. And what we think is happening in these cases is that because it is so fast, all that light must be coming from somewhere very, very close to the center. It must be somewhere very compact. It cannot be much larger than a few millilight seconds or light milliseconds. Okay, and we think actually that a lot of that variability must be coming from some new component that we actually haven't probed before. Maybe from these jets that I mentioned, which shoot out from close to the black holes. And these are thought to be maybe the inner parts of these jets are about 100 millilight seconds big or so. And so this might be able to explain some of this variability. But this is still a very active area of research. We are still trying to piece together why this happens. But what I want you to take away from this is that there's a lot of unknowns still in black hole research, and you have to be a detective in a way, because we only have so many clues. We can't see these objects in detail. We can't resolve them. So you have to use other indirect techniques like variability, for example, to try and infer the physics of what's happening in there. Okay, in my last slides here, I want to just end with a very short animation to show you what would it be like if one of these objects actually did enter our solar system. And this is just a very rough animation, but for example, this is a nice, bright, sunny day in Raipur, and then suddenly you see a big flash of light. Okay, and now I'm going to run a flashing animation. So if it bothers you, please close your eyes. There's going to be some flashes there. It might look something like this if there was a black hole in our sky. Okay, and of course it would be the variability here, as I said, has slowed down much faster, really extreme. Okay. I wanted to end with a poem that I really like. This is a poem written by a former lecturer, Rebecca Elson, who unfortunately died very young. But she's written a nice anthology of poems. And this one says, "We astronomers are nomads, merchants, circus people, all the earth our tent. We are industrious, we breed enthusiasms, honor our responsibility to awe." And I hope in my talk I've been able to awe-inspire at least some of you. You feel this sense of amazing, something new and amazing and awe-inspiring. So if so, then I've fulfilled my responsibility. All right, so I'm going to summarize. I started my talk with several questions. What are black holes? Why are they interesting? Where are they? How big are they? And do they change? So I hope you remember, what are black holes? Black holes are the densest objects in nature. And they refer to causally disconnected regions of space-time from which even light cannot escape. Why are they interesting? Well, because just don't know how nature is able to generate such regions and what happens inside the event horizon. That's what everyone really wants to know. Unfortunately, that we have no direct evidence of what happens inside the event horizon, and we may never know. But we can, of course, theorize about what happens there. But not only what happens inside, but also outside the event horizon, the really physical conditions, is very high gravity, very strong gravity, very high temperatures, etc. We just cannot replicate in laboratories easily. So that's why they're trees for us. Where are they located? How big are they? And I told you that typical black holes in the Milky Way are several thousand light years away. Well, I said about the size of Southampton, something like 10 kilometers right? Yeah, 10 kilometers or 15 kilometers for typical black holes in a Milky Way. But there are also these monster black holes, which are found at the centers of most large galaxies. So supermassive black holes, which are millions of times bigger. Do they change? Yes, they can change a lot. They grow by accretion of matter, steady accretion of interstellar gas and dust, and also by mergers. I showed you examples of both. How do we study them? Well, we study them by looking at actually the plasma which is around them, the hot gas plasma that either falls in or actually is coming out of that environment. And we cannot see it once it crosses the event horizon. So all the plasma that we see is just outside the event horizon or on larger distances. The plasma emits a lot of energy. We still don't fully understand how. We have some theories of it. But because these are so distant, we actually study the light variations from many of these objects to provide fundamental information on their sizes and the physics that's happening in there. And these variations can occur anywhere from milliseconds to years. All of these variations give us different clues as to what's happening. And we need many different telescopes to be able to understand the full spectrum of what's happening. Multi-wavelength astronomy, as you heard before, is very important for us. Black holes still remain mysterious in many ways. They are the densest objects in nature, and it's a very exciting area of research. And with that, I'm going to stop, and I will take your questions. Oh, yes, and these are to the feedback form, so you can either use the form, the link there, the office form at the top, or you can use a QR code. It'll take you all of 3 or 4 minutes to fill in this survey, and that'll be really appreciated. Thank you. Thank you. I'll be happy to take any questions. Okay, good question. So basically, after supernova, the time scales are very short, very quick. It can happen in the matter of seconds. Basically, you have to remember that there is very, very strong gravity inside a star. Okay, and all that gravity is being balanced by radiation pressure from inside. All the heat, light from inside the star is balancing the gravity, stopping the star from collapsing. But once that heat and light finishes, it's gone, then there is nothing to prevent the collapse of the star. And this you can actually calculate. It's a relatively simple calculation. What is the free fall time of something like gas from, say, the surface of the sun down to the center? Okay. And it is actually very, very quick, just on a matter of a few seconds or tens of seconds, etc., depending upon the size of the star. तो यही सोचते हैं हम कि ज़्यादा टाइम नहीं लगेगा बिल्कुल भी. It should really be instantaneous. We still need to prove this, of course. We don't have definitive proof of it, but all our theories point to the fact that it should be instantaneous. And what we see is, in supernova explosions, we see this enormous amount of energy coming out. A huge amount of energy must mean that, and not only energy, actually it's huge amount of power. So energy divided by time. The time is very, very short, which means that the power is very, very large. And so because it's so rapid, this release of energy, that's also why we think that the black hole is formed almost instantaneously. Sure. You mean accretion process? Yeah, okay. Yeah. So a star or a black hole, I will tell you. Yeah. So yeah. So typically speaking, well, actually, I'll have to go back here. So we are talking about roughly, if you think about it, so 10 light seconds. So 1 light second is what, 300,000 kilometers, 3 lakh kilometers. Is that right? Yes. So this must mean it's 30 lakh kilometers, roughly speaking, between a star and a black hole, roughly speaking. Okay, plus minus a few 10 lakh a few 10 lakh kilometers or so. We don't know of any planets around black holes, although there are actually indications that some of these systems might have additional other bodies, not just one star. There could be planets as well. I think that's very exciting. It still needs to be proven in detail. But I think the planets must be farther out. Definitely, at least well, a few times further out, if not more. Because if they come very, very close by, then they will be torn apart by tidal forces, basically, or other instabilities. So they must be somewhat further out, I think. Is that sure? Good evening. Yeah. Okay, good question. We don't know. That's the short answer. But the long answer is that it just depends upon how much, how many times this merger occurs. Okay, so what do we need? We need to start from something like. Let me share my screen again. I think this is good. Okay, so we need to start from something like a stellar mass black hole, maybe 10 solar masses or something like that. And then we need to end up with 10 million solar mass black hole, right? So how does this process happen? The process happens by lots and lots of mergers over the time of the growth of the galaxy, growth of the universe as well, and also by accretion of matter, this steady accretion of matter. So we think that this process it can happen, can be quite frequent. The mergers can be quite frequent in the centers of galaxies, because at the centers of galaxies, there's very high density of black holes, etc. So there can be encounters, lots of mergers happening in the intermediate mass black holes, which then merge again, etc., etc. And then also when two whole galaxies collide, the two black holes, their own supermassive black holes, can merge and form even more massive black holes. So I don't have a single answer for you, but the process definitely takes a few 100 million years or so, or a few billion years even. But it's still unknown. And it's very interesting because recently, with this JWST telescope and some other telescopes, people have found very, very massive black holes very soon after the Big Bang. So the Big Bang happened 13.7 billion years ago or so. And then very soon after that, maybe a few 100 million years later, we already find supermassive black holes, big supermassive black holes, which are present. So how did that happen? Well, we don't know in detail. Somehow, the formation of these supermassive black holes seems to be very efficient. It could be, there could be other processes like primordial formation, which I'm not going to talk about here. But basically, there must be some process in nature which can easily form these supermassive black holes, and we don't know what that is. Sure. Please do fill in the feedback form while you're asking questions. Hello. Evening. Yeah. Okay. So good question. Basically, we don't see the black hole itself. We never see black hole. We can only see either light from around the black hole, like this. Okay. Or there is one more technique that we can do, and that is actually, I don't think I have a slide for that. Do I? No, I don't. The other thing that we can do is to actually measure the gravity of the black hole. Okay, so you can imagine this star is orbiting this black hole. So it's going around the black hole. And because this black hole is very massive, the orbital velocity of the star must be very large. Okay, I hope you know formula, simple formula, for example, for orbital velocity, something square, example, point. So if you imagine m is very large, the mass of the black hole is very large, r is very small, the separation. So that means the velocity of the star has to be very high. So if we can measure the velocity of the star using spectra, you can actually measure the spectrum of the star, changing redshift, blue shift, redshift, blue shift. Then you can actually work out, you can compute just using simple Newtonian, Newton's laws of gravity. What is the mass of the black hole by measuring the velocity, and if you know the star type, etc. So by doing such measurements, we can confirm that even though we cannot see a black hole, there must be a black hole which is present in these systems. That's the only explanation for many of these objects. And in fact, all of these objects that I showed you here in this graph, every single one of them has been confirmed. They have been confirmed by this radial velocity, blue shift and redshift change. Masses of all these objects have been measured. They all host black holes. तो ब्लैक होल नहीं दिखता है, लेकिन उसका रेड शिफ्ट और ब्लू शिफ्ट मेजर करके यू कैन एक्चुअली वर्क आउट कि उसका भार कितना होगा. आई होप दैट्स क्लियर. Yes. Great. Excellent. No, thank you for the opportunity. Hello, Nand. Right. Okay. Okay, brilliant. My pleasure. Thank you. All the best. I can see the students now. Thank you. Please send me a photograph of the students. Thank you. Bye. All the best.